Before we get going, let's remind ourselves of what we have so far. To describe rotation, we specify three quantities. The angle theta tells us where we are rotationally. Omega, the angular velocity, tells us how fast the angle is changing. And alpha is the angular acceleration that tells us the rate at which the velocity is changing. And if we have a situation where alpha isn't changing over time, and we can connect up these quantities with a set of kinematics equations that look exactly like 5 old friends of ours, except they're written in Greek. Kinematics describes motion, but recall that we have a bunch of ways to understand why objects move from one place to another, and help us make predictions on how or when. It turns out that we can bring a lot of these same ideas into the conversation about the way that things rotate. Right now, we're going to talk about Newton. In translation, we have Newton's second law to tell us how much acceleration we will experience. And it turns out that if we have something that's rotating and we want to know the angular acceleration, there is also a Newton's second law for rotation. Alpha equals tau over I. Tau is the torque. Now, most people, when they hear a physics friend say force, they have a sense of what force is because we use the same word in physics and in normal life so that we can connect the word force with a felt experience of force. On the other hand, the word torque may feel foreign. Even if the word sounds unfamiliar, pretty much everyone has applied torque, say when opening a jar of pickles, or felt torque being applied, like if you're holding a doorknob and you can feel someone, maybe your brother or your sister, trying to turn the knob from the other side of the door. You can think of torque as twisty force. To understand torque, let's imagine that we have something that could rotate. What would cause our object to start turning? We need a force. The force is crucial. No force, no rotation. But rotation is subtle. It turns out that force alone is not enough. It matters a lot where the force is applied. If you think about it, there are locations where we could apply all the force we want, and we still won't get any rotation. If the torque is a twisty force that causes rotation, then when we compute its value, we have to take into account the force and where the force acts. The torque is equal to the tangential component of the force multiplied by the moment arm, the distance from the axis of rotation to the place where the force is applied. If the force gets closer to the axis, then the moment arm gets shorter and the torque is less. Torque is the way physics describes what people mean when they talk about leverage. Long levers turn things more readily than short levers because the force acts farther from the axis. Here's the conceptual parallel. Acceleration requires force. Change in rotation requires torque. But acceleration is mediated. And if mass restrains force, what is the equivalent in the physics of rotation? This quantity is called the moment of inertia. It may sound new to you, but everyone has experienced the moment of inertia. It's actually a familiar concept, even if we don't normally use the term. Let me show you. Suppose we had a balloon and a bowling ball. They're the same size, but one is more massive. And you try to spin the balloon and then spin the bowling ball. Which one requires more effort? Okay, you probably don't have to think much about it, but the difference between them is that one has a high moment of inertia, making it hard to turn, and the other one has a low moment of inertia, making it easier. Why are they different? Because they have different masses, and in the rotational inertia, mass matters. But it's not the only thing that matters. The next imaginary experiment is with a baseball bat. Imagine grabbing a bat and rotating it around the axis like this. Think about the feeling in your hands. How much effort does this take? Okay, now think about rotating the same bat but in a different place. Again, use your mind to judge the feeling of the imaginary bat in your hands and ask, how much effort does this take? Does it take more effort or less effort than the last one? Okay, one last change. Try rotating the imaginary bat around this axis. Does this take more effort? Less effort? Okay, now compare the effort required to make these three different rotations of the imaginary bat. Which one is hardest? Which one is easiest? If you need to think about it for a moment, pause the video now. Let's see if we agree. Why does it feel so different to turn the same bat around different axes? The bat's mass isn't changing. This experiment shows us that when deciding how hard it is to rotate an object, it's not just the amount of mass, but also the location of the mass, which matters. In fact, the distribution of mass turns out to be more influential than the amount of mass itself. Let's look at the simplest possible case. If you look at one little chunk of mass that's going around at the end of something light and stiff, like a bicycle spoke, the rotational inertia is the mass times the square of the distance away from the axis. That quantity, I, the moment of inertia, is the degree to which this object will resist any torque tending to make it go around this axis. Ready to put it all together? Yeah, baby. Here's Newton's second law in its angular form. If it looks weird, then take a little deep breath and remember this is just your old friend, but written in Greek. You see it now? Acceleration's on the left, and on the right, twisty force over twisty mass. Okay, we know what torque is. It's the force times the distance from the axis. And we just said that rotational inertia is mr squared, so let's make those substitutions. Okay, I see some r's we can cancel. And speaking of old friends, F over m is its own thing. But wait a second. I think if we kick the r over, then do you see what this is? You remember what r alpha is? It's just the darn acceleration. Are you kidding me? Wait, we went through all of that just to get back to Newton's stupid old second law? Really? You know what the problem is, right? This is the problem. You see it? Do you know what that is? You too, don't you? It's a point mass. We know the physics of point masses. It shouldn't surprise us that F equals ma. But the point of rotation is to study things that are not point masses. Extended bodies, objects where the mass is not all in one place, objects where the mass is spread out. It has distribution. In other words, extended rigid bodies. Yeah. Okay, let's take another look. Same song, different verse. For a point mass, the moment of inertia is mr squared. What about for an extended body? Well, an extended body is just made up of point masses, or at least parts that could be approximated as point masses. In the same way that we could add up masses, we could also add up rotational inertias to get the inertia of an entire object. You can see where this is going, right? More parts means smaller parts. Smaller parts are more point-like. We could do this again, breaking the object into 15 or 20 or 50 parts, and each time we make more parts, the value of the inertia gets more accurate, and pretty soon, well, you can probably guess that pretty soon calculus is going to want to poke its nose in here. If we really want to make an accurate determination of the moment of inertia, we ought to separate the object into increasingly large numbers of subunits. And if we want a large number, infinity is very large. And yes, absolutely, thank you, Mr. Calculus. We know that you are very good with infinites. But I'm not sure that we want to have to use integral calculus every time we rotate an extended body. So here's something interesting and happy. You know how we find the moment of inertia? We look it up. Seriously, in a book. Every physics text that addresses the question of rotation has in it somewhere a table that lists the moment of inertia for a routine set of basic shapes. And yes, calculus lies behind these values, but in the vast majority of times that we want to know a moment of inertia, we don't do the calculus, we just look in the table. If we can make a good match between our real-world object and one of the ideals in the table, we just use the ideal value. Now we are ready to do a rotation problem for real. So here is what I'm going to ask you to do. You're going to pause the video while you go get paper and pencil and a calculator, and then you are going to solve the problem. I'll give you a couple of suggestions while you go, but the idea here is for you to solve the problem. So pause the video now and go get your stuff. Seriously, if you haven't paused at this point and you're thinking, I'll just let the video play, well, you're missing the point. Seriously, okay? Pause the video. Okay, good to go? Got your stuff? Okay then. As we go through this problem, I will suggest the tool that you need for each step, but you're going to do the algebra and make the actual calculation. I'm not going to leave long blanks in the video, so pause the video as we go so you have some time to compute. Okie doke. First, write Newton's second law in its rotational form. Now, find the value of tau. Next, we're going to get the moment of inertia for a solid sphere. How do we do that? We look it up. Seriously, get your book, hunt up the table of I values in the rotation chapter. You're going to want to know where it is because you're going to be looking at it frequently in the future. Maybe put a sticky note on that page or something. Anyway, if you don't have a book, search the interwebs for a table of moments of inertia. In any case, go get the I value for a solid sphere. Okay, here it is. If yours looks different from this, check the table. Maybe you looked up a hollow sphere or a thin-walled sphere instead. We want a solid sphere. Once you've got the inertia and the torque, you should be able to determine the angular acceleration alpha. Pause the video now while you find alpha and start it up when you have a value. Now that we know the rate at which the rotation is accelerating, you can find the angular speed after 1/4 turn. Go compute that. Final step. What is the speed of a point at the equator? We are there. Do you have an answer? Does it agree with this answer? If it does, awesome. You've just done a rotational Newton's second law problem. If it doesn't agree, go back and try it again. Just, I don't know, check your math, do the algebra, whatever it takes. And the takeaway? We have two regimes. Translation, the question of an object's position, and rotation, the issue of its orientation. We can connect one regime to the other using these equations. Now, the same way that we have translational kinematics that relate displacement, linear velocity, and acceleration, we also have rotational kinematics that relate angle of orientation to angular velocity and acceleration. Just as we have a Newton's second law that tells why position changes, we also have a Newton's second law for rotation to tell the story of changes in angle. The torque we find from a combination of force and where it acts, and the rotational inertia, we look it up. Okay, that's it so far. Now go forth and conquer.